All right, good morning. So today is the last day of lectures. It's going to be lecture number 26. We'll discuss about active learning. For many of you, today is also the last day of the course. So if I think most of the grad students have chosen the project options, which basically means that when you submit your report today, so that should be the end of your everything from within your coursework. Of course, if you're doing the extra credit, then you have one more day until tomorrow evening to submit that. But apart from that, everything else should be done. In terms of logistics, for those of you who have chosen the final exam option, it's going to be there on May 1st. Very similar to before, except that instead of being a 75-minute quiz, it's going to be a 90-minute quiz. You can choose any time interval between 8 and 11 on that day, on May 1st. So this is only for in-person students. Again, you don't have to come here to the classroom itself. You can take it from anywhere. It's going to be online and on Canvas, similar to before. I'll also post the instructions on Piazza, like a couple of days or something prior to the May 1st deadline. I'd hope to have published by today evening the quiz. I'm not sure. I don't think I'll be able to do it today, but maybe tomorrow or day after I should post it on Canvas. So you'll see under your exams tab, there'll be a quiz that you can take. But of course, you can't take it. It won't be, you should see it on Canvas, but you won't be able to take it until May 1st. Everything that we have covered from lectures 1 to 26 will be part of the quiz. Again, you have to be a little bit more intelligent in terms of where you're allocating your resources in terms of studying for it. More of the questions will come from the stuff that we covered after, let's say, quiz number 2. So something like, I believe autoencoders is what we started off with, but maybe parts of CNN as well. So anything with respect to stuff that we have done after CNNs, you can expect a larger weightage of questions towards those concepts rather than the previous first things. What else? So it's, again, similar to before, it's going to be conceptual quizzes, which means that you don't have to essentially have any kind of coding requirements or calculators, yes, but very simple calculators. You really don't need access to like very big formulae and stuff like that. It's going to be open book as well, so you should have access to all the notes during the exam itself. Regarding the homework, so for today, instead of me having an office hours, it'll be Jorge who will have office hours. It'll be an additional office hours for him. So today from 12 to 1, he will have office hours, and essentially he is going to tackle any questions regarding homeworks. So anything from homework 1 to 6. I believe half the homework 7 was graded yesterday itself, but I'm not sure if it's out yet for everyone to see. But hopefully by the afternoon today or evening, you should be able to see homework 7. So ideally, we want to have everything, at least from homeworks 1 to 6. All issues have to be corrected today itself. Yes? You can ask him, but I believe it's virtually. So which the link should be on Canvas. This thing. So any homeworks, any issues that you have, any issues with quiz. If you have an issue with quiz 1, quiz 2, please send me an email or a private message on Piazza. I'll try to correct it. But anything with respect to the homeworks, please contact the TAs. Please contact Jorge today and try to complete and try to clear any question that you have, any concerns that you have with him. Because we'll try to finalize. Again, for many of you, the course will end today as soon as you submit the project report. So we'll be finalizing the grades very, very soon. So we need to make sure that all the homeworks, all the quizzes, all the points that you have got is set right. So homework 7 itself for the distance learning students, again, it's due tonight. So that means that we will take probably whole of tomorrow in order to grade it. And you should ideally have the grades by end of tomorrow. But again, by Wednesday, try to make sure that all your questions are all your questions are cleared before this Wednesday for homework number 7. All right, so in terms of project, it's going to be due today at midnight. Again, we'll have to go through and grade it, and it's going to take us a couple of days. Couple of you have approached me regarding, okay, you might not have you might have tried what you wanted from the progress report, but you did not get good results. So you kind of shifted to a different concept, and that's perfectly fine. The goal of progress report is not to box you in to a certain idea, but rather to make sure that you have a plan to start with. So if you have changed your plans from the progress report to the final report, it's perfectly fine. I'm not mandating any kind of content except the fact that I need this one summary basically of who has contributed individually towards the report. Again, this is not an easy thing to do. It's very esoteric, but some of them are quite easy. Like, okay, person 1 wrote the introduction, person 2 wrote the results, person 3 wrote the literature review. These kind of things are something that you should be able to put in the report itself. We won't be grading based on how your results are compared to, let's say, SAM. Again, this was a 1 month, 1.5 month, 2 month project at most. It's not easy for you to have gotten like 90-95% accuracy. That's perfectly legitimate. So we'll be looking at the novelty, the kind of problem that you have set up, the metrics that you're using in order to say that your problem is essentially on the way to be solved, future work that you would like to do. Based on the results that you have currently, if you were given another 1 month, let's say. Those are the kind of things that we'll be looking towards towards creating your grades, rather than just looking at the results and saying that, okay, you got 95%, but the original result was 90%, let's say. So that's not something that we'll be grading you on too much. Lastly, if your results are easier to be shown as a demo, please do so. In that case, you wouldn't have to write anything in the results section, the discussion section itself. You can just post a video, essentially, of your results. Now, there was a couple of questions yesterday on Piazza about the grading logistics itself. The goal was never to have the extra credit as well as the project. So it's not like it would add on to each other. For 8803 students, it's pretty straightforward. The project is part of your syllabus, so it's something that you will have to do, and extra credit is something on top. But for 4803 students, it was either or option. So basically, if you have done the project, then that means that's going to be adding 20% to your grade. But if you have not done it and you still want some extra credit, then you can do the extra credit option, which would be 10%. So the labeling for extra credit is harder, as you might have seen if you have worked on it, which implies that it would be worth about 10% of your final grade compared to something like doing the phase 1 project labeling, which is much simpler. So that would be worth about 5% of your final grade. It's worth 1/4 of your total project, which translates to about 5% of your overall grade. All right, I think I covered everything I wanted to in terms of logistics. Any questions before we move on to the lecture itself? All right, great. So today, as I mentioned, will be the last lecture. We'll continue with what we started off last Wednesday, which was about the idea of this data and label efficient learning. So whenever we have talked about supervised learning, it has always been the idea that we have access to a very large data set, 1 million images, the labels exist. Let's say on an imaginary data set, and I can train a very deep architecture, a very large transformer model, billions and maybe billions of parameters essentially, and I can get a very good set of results. But doing this has some costs. Or many of you have done the labeling in the project, you know how difficult this kind of annotation process is. So it's not easy to always have access to this large amount of data. The question we have been tackling from last week has been, how can we address this in terms of having a very good model, yet with some kind of acceptable cost in terms of the time effort that human annotators put in. So labeling assumption in supervised learning has always been that the labeling has already been completed. But today we'll be discussing something called active learning. And the assumption is that samples are selectively labeled with certain budget constraints. So in the beginning, when you start doing your training procedure, you'll have access to a certain amount of budget constraints. And what those budget constraints are, we'll discuss in a little bit. And based on these budget constraints, the goal is to select the samples within your training set to label, which implies that you start off with, let's say, 1 million images. None of them are labeled. Your goal is to then select about 10,000 images for labeling process. That means that you need to select the best 10,000 images for labeling. And the question then, the research question then, is going to be what this best implies. So everything that we'll be talking about today is about this selectively labeling, this considering or finding the best possible images in order to do my labeling procedure. So the first few slides are this from a motivation perspective. Let's say you're trying to differentiate between a fish and a toad and a frog. So let's look at it from literally a cost analysis perspective. If I were to label each of these samples, each label would cost me $3, let's say, if I'm using a third-party company to do so. But your available budget is only $9. And now that basically means that you only have 3 of these images for labeling. You can only give this data set out and expect only 3 images back. So then the question would be, which of the 3 images? So you have all these are data points, right? This is 1, 2, 3, 4, 5. There's more than like 30 different data points here. But from this, you need to just select 3 based on the constraints that you have, which is your total budget, which is $9. So you can choose these 3 images for labeling, or you could choose something like these images here for golden images here for labeling. Or a third stage can be something like this. You have one from class 1, another from class 2, last one from class 3. Right? Now, again, you don't know the labels to start off with. So it's not like you can pick one image from a particular cluster, another image from another cluster, another image from a third cluster, and so on. You're just given raw images to begin with without having any knowledge about what the labels are. Right? So the goal now is to see which is better. Is it selection 1, selection 2, selection 3? The entire goal of active learning is this idea, is which set of images should I label in order to ensure that I have the best possible algorithm that I can learn, best possible model that I can learn. So which selection results in the highest performance of our machine learning model is something that we are interested in terms of this setup. So if I'm asking this question here on the bottom right, what I'm in fact doing is a different paradigm of learning, which is called active learning. So supervised learning, you have access to all labels, we learn it. Unsupervised learning, you have access to no labels, and we want to learn something out of it. Self-supervised learning, we create these pretext pseudo tasks that will help us create pseudo labels, and based on a much smaller set of known labels, we'll be able to train our model. The goal in active learning, it's a very it's a very nice topic because the roots are in fact from a very theoretical perspective. The definition of which selection leads to highest performance, what the best subset is, has a very, very, very theoretical background. It comes more from a theoretical perspective, but there's a lot of deployment opportunities as well. If you go to the industry, it's not like you'll ever start off with a very large set of labeled data. You start off with a smaller set of labeled data, and it's a process. Continuously, you're getting more and more labeled data. So if you can say which among the data points is the ones that you want labels for, then it's going to be very helpful in terms of getting your, in terms of kickstarting your project and your model very quickly, rather than waiting until the very end when you have all available images and data points. So this paradigm where you're selecting images is what we call as active learning. All right, so let's just go through very quickly the process itself of active learning. We'll go through some of the fundamentals, which is the basics and the overview. So I start off with this large data set, which is an unlabeled pool. I'm now going to try to leverage some model. Now, at every single instance, if I ever say model, this can refer to all the models that we have talked about before. Active learning is something that existed before deep learning algorithms. So anything with respect to, let's say, GMMs, k-means, anything we have talked about before applies when we talk about active learning in today's lecture. So we want to leverage information extracted from the model to guide the selection. So selection is not arbitrary. It's not random. I don't simply say that, oh, these look the best images, hence I'll use them in order to do the labeling. No, it's a much more involved process where I'll use my machine learning model itself to tell me which is the most important sampling. And that's where the word active learning comes from, or at least the word active comes from. Your model is not a passive bystander where it's just letting you feed in all data, all millions of images, and spitting out some results. It's actively telling you that I need these 10,000 images out of the entire 1 million images for me to train myself the best. So it's giving you a very in-depth look at the information that it's able to extract, the uncertainty that it's able to extract, and based on that, you can then say that, okay, these are the best samples for me to label. So the word active comes from the model perspective, where the active is, the model itself is active in the process of training rather than just being trained on, essentially. So once you use this information from the model, you select the data points, and then you say that, okay, these are the 3 images right now that I need to label, and you would go through the labeling process. So if you have ever heard the terms human in the loop with respect to these kind of machine learning algorithms, this is one of those algorithms where you have human in the loop. So till now, our backpropagation strategy, everything in that involves training is something that automatically happens. Once you click that run button, it keeps on working, and there's nothing, if a stopping criteria is met, that is when the algorithm training is going to be done. But in this process of active learning, there is a requirement that these images have to be labeled. Right? So that basically means that a human annotator exists in the middle. They are going to go in and label these 3 images, and you have these selective labeling. Right now, this image is labeled, this image here is labeled, another image I think somewhere here is labeled as well. So these 3 images are labeled. What happens now is that it is a continuous process. It's not like we talked about budget being $9, and then these 3 images, right? What if then we increase this to $20 or $24? That means that this is happening in a round. That once you have these 3 images labeled, now you say that, okay, my learning model looks good. You have gone through the proof of concept. Now I want more deployment, which means that I'm increasing your budget from $9 to $24, which now implies that this is now going to go in a loop. That is that once my $9 is done, I need another, or I have another $15 to spend, which basically means that I have about 5 more images that I can label. So I can now go through, and this now acts in a loop where I'll be able to label more and more images based on the constraints that I have. And this is the active learning workflow, essentially. Let me go through some of the terminologies here. So the large set of unlabeled images, generally we call it as an X pool, where this is a pool of unlabeled images that we have. X-train is the images that have been labeled. So in the beginning, I labeled 3 images, right? So that is now part of X-train. But then in the next cycle, next round, I'll have access to 5 more images in the training set. So in total, now I have 8 images. So that basically now my X-train from 3 has now become 8 by the addition of this 5 images. A is some kind of an acquisition function. So if I were to choose, there's multiple strategies for choosing what the best set of 8 samples or 3 samples is going to be. And that strategy generally is termed as acquisition function, or sometimes it's also called a query strategy. You'll see both in literature. Last is NB, which is the acquisition size. So in my first round, it was 3. Based on my example, in the second round, it was 5. Generally, this remains constant. Like, if it's 3 in the first round, it's going to be 3 in the second round, 3, so on. It's just easier and for us to manage notations and so on. But essentially, when we talk about NB, it's the acquisition size per every round. Let me go through the process in words very quickly before I can stop for if anyone has questions. So the process in active learning goes something like this. Our input is essentially a large unlabeled pool. Let's say this is 1 million images, which is our unlabeled pool. I have access to no labels across this thing. I have an untrained network to begin with. That is, it's just you've used some kind of initialization and just created an AlexNet or a ResNet 18 architecture. You've really not trained it. We need an acquisition function, and we need an oracle or an annotator. So if you look at the literature, one of the words that is commonly used instead of annotator is also an oracle. because at least when we write research papers, we already use existing data sets to it. So that means that we assume that we have no labels, but in fact we do have labels. So you don't need a human to actually do the annotation in the process. You're just using an oracle to tell you at every single instance what the label is going to be. So let's start with round one. In round one, we choose a very small and random subset of available data from the unlabeled training pool. So let's say I start off with 1 million images. My random subset generally is just a single batch. I'm going to use 128 images. In ImageNet, either 32 or 128 are common numbers that we use for batch sizes. So I'm going to use, let's say, 128 images. I'm going to choose 128 images and ask the annotator or the oracle for the labels, and I'm going to get the labels. So we label the randomly selected subset, and we train an ML model based on just the 128 labels. The 128 images. Again, we have access to 1 million images, but all of them are unlabeled. We are only going to be training it based on 128 images in this particular case. So this is round number one. Round number two is we'll pass the remaining unlabeled data through the trained ML model. In other words, what is 1 million minus 128? It's like 999,000 something. So all the remaining images, I'm going to pass it through the trained ML model. And the acquisition function right now selects a subset of data from the unlabeled pool based on the outputs from the trained model. Again, the machine learning model is not a passive observer. It's actively trying to influence my acquisition function. It tells my acquisition functions that I need these 1,000 images to be labeled. Right? That comes from the network. So there is some kind of an output from the network that we are going to use in order to say that my second acquisition function, let's say subset of data, I'm going to choose 1,000 images right now. So I want my acquisition function to get 1,000 images, and once I have that, the annotator or the oracle essentially labels these 1,000 images, which means that my xtrain at the end of round two, has about 1,128 images. 128 images from round one and 1,000 images right now. Now, the ML model is now retrained based on all the 1,128 images. And the exact same thing happens again in round three. So now I have about 1 million minus 1,128 images in my unlabeled pool. I'm going to pass all of these images through my network. I am going to obtain some kind of outputs from my network, and my acquisition function is going to use this outputs from the network in order to select the next 1,000 images for the subset for training. Right? You keep on doing this until a particular constraint is met or a budget is met. I'll talk about what this constraint of budgets are in stopping criteria in the next part, which is basically the performance metrics. Any question about the process itself of active learning? Yes.
So when we were talking about the different clusters, it seems like the small subset that was chosen was not random. It was selected based on certain criteria.
Mm-hmm.
You're saying that was just random, that they happened to be from those three clusters?
You mean, so this was more of a motivating figure to show you that there is going to be that if there is some constraints, I want to be very selective in what I choose. So this was more of a motivating figure. Right now, we don't know anything about the cluster. We don't know if clusters exist. I'm just given million images. I don't even know the number of labels that there can be 1,000 classes or anything like that, right? You need to know that in order to construct your network, but still, you have no idea what belongs to what. You have no idea where the clusters are, so you start off with random. So the 128 right now are completely random, and you have no clue as to what clusters they belong to, which is fine, because the goal is now to keep on going through rounds until a certain criteria or a budget is met. So there you'll start seeing that the results become more better. Okay. It'll become clearer when I talk about the first strategy, but basically, let's say I've trained my function, my neural network, with 128 images. So that means that when you pass the remaining images through it, you get the final logits, right? So I can get some kind of a softmax confidence out of it. I can order the softmax confidence of all the 999,000 odd images, and I can select the ones which have the lowest confidence, and I can use them and say that, okay, my acquisition strategy then is going to be that lower the softmax confidence, more difficult this particular sample is for my network. So let me train it. Let me label it and give it to the network for training rather than for it to be inferencing, basically. So one strategy is basically to start labeling everything that is very difficult so that the network can start learning better.
Is this a very time-intensive process?
Not really. It'll be worse if, okay, let's take the ideal case where you have 1 million images, they are not labeled at all. So you start by asking the Oracle to label 1 million images for doing normal supervised learning. But in active learning, what you do is you ask the Oracle to label 128 images, take a break, then label these 1,000 images, take a break, then label another 1,000 images, take a break, and so on. Ideally, you will never get to a stage where the Oracle needs to label 1 million images. You'll realize that somewhere at around 40,000 images, you have already reached the optimal performance. Because this is similar to the support vector machines that we very early on discussed, which is maybe that you don't need access to all these things. You only need a few samples, this, in order to construct good classifiers rather than using everything from before as well. So the goal, I shouldn't say the goal, the hope is that before we reach the entire 1 million budget, we will be able to find the best possible performance much before we reach that. Not really. In dropout, essentially, what we are doing is, are you asking dropout from the perspective of the network, or are you saying that this is similar to dropout in the data rather than dropout in the network?
I guess it is more the data.
Yeah. So you can think of it as a dropout with respect to data, but I'm not sure what the analysis there would be. Once you have selected your data, it's exactly the same as supervised learning. So there's no difference at all. So it's not like we are saying that in round number 1, we are using this amount of data, and in round number 2, we will lose this data and look at only the next set of subset. No, we are adding to the subset and we are increasing our thing. Dropout is best understood through the lens of like regularization. There are a couple of other ways in which we can understand dropout in terms of Bayesian neural networks, but regularization is the one that I think we are all familiar with. But the idea of active learning of selecting subset does not do either regularization, or it's not seen through the lens of either regularization or through Bayesian neural networks. All right. If there's no other questions, then let's talk about the stopping criteria. There are 2 major criteria that exist within literature. One is the performance criteria themselves, and another is the annotator criteria, which is the time and the money. Let's start off with the more simplistic one, or the one that I think every one of us will understand and have seen before, which is the performance constraints. The idea is that we want to make sure that with a smaller subset of labeled data, we'll get similar results as, let's say, a fully supervised learning algorithm. So let's look at this particular graph here. The x-axis is the number of annotated samples in xtrain. Again, if we have 1 million images for training, usually this stops at around, let's say, 40,000 images. Generally, if you look at CIFAR 10, which you have 50,000 total images, it generally stops at 10,000. So about 1/4, 25%, 20% of the budget, you'll usually be done with these kind of learning strategies. So it is a stepwise function. So basically, this is at 0, round 0. We don't have a round 0, which means the performance is going to be 0. This here is going to be round 1. This is going to be round 2, 3, 4, and so on. So another way to look at your x-axis is the amount of rounds that can exist within your framework. The y-axis is some kind of a classification or some kind of a metric for your performance metric for your application. So if it's classification, then this can be something like it could simply be accuracy, or it could be a F1 score, the true positive rate, the true negative rate, false positive rate. Everything that we have seen for classification performance can now exist on the y-axis over here. For object detection, for instance, it's going to be something like mean average precision, which is the number of times you have made sure that the instance that you're looking at has existed within this framework. Another very important part here is that the application-specific performance is on the test set. So till now, whenever we have mentioned about the idea of stopping criteria, it has been in, let's say, gradient descent, stochastic gradient descent, and so on. In those algorithms, we never assume that we have access to a test set. We have a validation set, and we say that based on this validation set, your gradients are less than a certain amount, norm of your gradients is less than a certain amount, or nothing has changed within the updating process. Hence, I'm going to stop it, right? But in this case, we are talking about the test set. In other words, what this means is that I'm going to go here and make a small amount of change. So instead of just saying that we have 1 million unlabeled pool, I also have a labeled test set to begin with. I'm going to train on my some budget of my 1 million images, but I still want to test on my test set. Or you can consider this as validation set as well. And I want to make sure that my results on the validation set is going to be similar to what I would get on the train set. So now if I go down to this slide here, let's say all my million images have been labeled. The result is going to be this dotted red line over here. So it's going to give you, let's say, 78% accuracy for these results. If I were to randomly choose across different rounds without actually having any kind of a good setup, without having acquisition function, let's say an intelligent acquisition function, I'm just randomly selecting 1,000 images at each round. The yellow line here, the orange or yellow line, is what I would expect, and generally it would be at the bottom, right? So if you try to analyze this, this means that at fourth round, the result is going to be, let's say if it's accuracy, the result is going to be something like 35%, versus if I choose some other better strategy, acquisition function, the golden line, for instance, my accuracy is going to be something like 55%, which is ideally what you want to see. If your goal in active learning is to design these acquisition functions, then you need to make sure that it's better than all the existing acquisition functions. So here it's a toy example. We are showing like 3 different acquisition functions along with all the data labeled as well as random acquisition. So in this case, you see that the golden line is much above all the other 2 ones, which is the green and the blue ones. So by looking at the area under curve, underneath each of these curves, you can see that AUC3, which is the golden line strategy, is much better than AUC1, which is a green, is better than AUC2, which is blue. Again, AUC is the area under curve. So essentially for the blue curve, that would be something like this. We'll be measuring this area and seeing how much this area would be. So that would be AUC2. Right? Does this make sense? So in terms of any questions here? This is very important. This is how we would say that acquisition function 1, 2, 3, and how we would differentiate each of them is based on something like AUC in this case. Yes? Good question. So in this particular case, let's say my training set has certain anomalies associated with it. So generally what happens is that, and by anomaly, I mean that if I go back to something like this, there'll be one image all the way over here, there'll be another all the way over here, and so on. So if I'm using something like k-means algorithm, for instance, this ML model is k-means. We already know that k-means is very bad against outliers, which implies that if I choose these kind of data points, which I would have to when all data is labeled, then my performance would be a little bit low. But if I were using an active learning strategy which has not chosen these 2 images, then my result would be higher because I don't have this anomalies is not messing up my training regimen, right? So essentially that means that there will be certain cases where your results is going to be better than if all data were labeled essentially. And that's why, again, this is a toy example, but this is how it would look like if that were the case in terms of anomalies. Yes?
Is there, for the test set, built-in representative of all the data points?
Generally, we don't want to have too much control over the test set. All we want from a test set is that it is balanced based on the kind of application that we are looking at. So if it's classification, I want to make sure that all classes are equally represented. But even that is not a requirement. The reason being that we expect our models to be deployed, and we want to make sure that it's not under our control what kind of data we'll be getting in. So generally, we don't do any. We do stress tests. So if before deployment, we want to make sure that everything is balanced. Everything is there are anomalies. We are taking care of anomalies and so on. But after deployment, we don't want to put any constraints on top of the test data itself, that it has to follow, let's say, X distribution or Y distribution and so on. All right, so this is about performance constraints, where y-axis is going to have this kind of test set based performance in terms of how well the acquisition strategy has done. The next is some kind of annotator constraints, and I talked about this particular slide before. Given just a sequence of 578 frames, people take an entire day in order to label this, because again, it's not easy. You need to make sure that this includes the quality assurance and everything, right? So it takes a large amount of time to label each of these data points. So our goal has to be that, of course, we cannot label everything if these are the constraints. If 578 frames takes 1 day and 10 hours, think about how much this is going to be on entire data sets or these kind of video data sets. Images are generally easier, but when it comes to video, it's very hard, because in the next frame when there's movement, you want to make sure that this particular box itself has moved to a certain instance. You want to make sure that the instance is also maintained. So there are data sets like video data sets where it's very, very hard. It takes a very long time in order to make these kind of annotations. So in that case, what we would have to do is have an application specific annotator cost on your train set, which implies that this here is going to be something like cost. It could be very simply put hours, which is that in this case, how much was it? It was 34 hours, right? So if one round had just one video sequence, this would be, let's say, 1, then my some acquisition strategy here would be 34 hours, essentially, right? This is what we are currently looking at, where the y-axis is in terms of something like hours or flops, which is the amount of work that your network has had to do in order to train it, or it could be literally in terms of dollar cost, but this is usually not preferred, especially in research papers, because you don't have control over who you're using in order to create this data set. It could be a very expensive company or not. In fact, I've never seen a paper with dollar costs in their graphs. You usually see it when people are trying to market their companies, saying that we have started this startup for annotating data, and we give you at a much lower price compared to others. You can see it, but generally this is not preferred. I've never seen it within research papers. What is usually seen, however, is hours, or even better still, something like flops, which is the floating point operations. Usually it's seen in GFlops, which is gigaflops, the amount of computations that needs to happen within, let's say, round 1. Right? Round 1, if I have something like 10,000 images, or I think we talked about 1,128 images, then the amount of flops, which is the number of floating point operations, is obviously going to be lesser than in round 2, where it is going to be something like 2,248 operations. Again, it's not just a linear scaling, because we are training deep learning models within it, right? So at every single round, you want to make sure that your gradients have become 0 or have become less than epsilon or something like that. So at every single round, the number of epochs, the number of rounds, the iterations is going to be different, which implies that the hours and the flops are going to be different. So flops are with respect to the network. Hours are with respect to the human annotators themselves. So if for 1,128 images, somebody has taken 34 hours, for 2,000, let's say 128 images, which is the second round, people might have taken like 95 hours, let's say for the next set of 1,000 images. So every single strategy will have a certain amount of Rs associated with it. Right? So that is how we'll be measuring this. And again, very similar to before, it's AUC. So AUC under this is actually, this should be the opposite in this case. I need to change the slide and put it in. So if I'm using Rs, right, the lesser amount of Rs that I spend for labeling, better it is going to be, which implies the yellow line here, in fact, is the best compared to something like the golden line up top. So I should have inverted this graph and put it here rather than copy paste the previous one, but hopefully you get the idea. My area under the curve in terms of the yellow line here, the yellow strategy here, is the best because it has the least amount of time that has been put in, or it has the least amount of flops, the floating operations per sample that has been, per second, sorry, which has been put in order to train the network. Right? So it's the opposite of what we had before in the performance-based constraints, which is we wanted to maximize our performance, but here we want to minimize our annotator costs, which is either in terms of hours, or we want to minimize the operations of our network itself, which is in terms of flops. Any question here? All right, so if not, we'll move on to the next part, which is we'll talk about the acquisition functions themselves. There are three sets of acquisition functions, which are difficulty-based active learning, diversity-based active learning, and a combination of these two, which will be fusion-based active learning. We'll look at about 3 of these strategies in the difficulty-based acquisition functions. We'll look at 2 strategies in the diversity-based acquisition functions, and we won't look at any strategies in the fusion-based itself, but rather just a motivation of why we need this kind of a fusion-based strategy. Finally, we'll talk about some other metric that has recently become more problematic, which is regression, or probably I should call this performance regression, so as not to confuse you with regression, what we had talked about before. All right, so let's start with the first one. So currently we'll be discussing about acquisition functions. Until this point, I've just said that there is going to be some methodology that is going to select the best 1,000 images or best batch size of images for the Oracle to label. Right? So now the goal is to try to understand, okay, how can we construct these kind of acquisition functions? The first large set, if I were to take all literature that exists and try to categorize them, these are the 2 things that I'll be able to look at, which is the difficulty-based or the diversity-based. So the difficulty-based acquisition functions, as the name suggests, it's basically we are suggesting the most, we are taking the most difficult samples in order to label, which implies that given this kind of data, I'm going to choose this as my samples to label. Apparently this one as well here, as my samples to label. Anything that exists, that might exist far away from your classifier is not important according to these strategies. So some of the difficult samples are rare classes, outliers, high data noise, class imbalance. And if you read through the literature, sometimes these are also called as uncertainty-based acquisition function rather than difficulty-based. But generally, they try to tell you the same thing, which is that given a large amount of data, if your goal is to select a subset of data for labeling, then it has to be the ones which are either the most uncertain or the most difficult for a particular network to label. We look at 3 strategies within this as examples, which is going to be entropy, least confidence, and margin classification. Now, all of these should be familiar terms to you. Entropy comes from the probability theory. Least confidence and margin. Margin is a margin classifier that we started off with, talking about the support vector machine question. So in this particular case, I'm not assuming access to a neural network. And generally, when we talk about this, we are looking at it from like literally an input space, and so you could consider them as a PCA. But creating these graphs was just as a toy example rather than exact data that can exist. All right, so we'll start off with entropy. Very simply put, entropy is the information, the surprise that exists within your data for a given network. So that means that if I give a data point and let's say it's a 10 class classification, every single class has a 10% probability. Right? So that means all logits are probably showing you the exact same numbers, which implies that you're really not learning anything from this data point at all. Or maybe I shouldn't put it that way, that this data point has the most amount of information because it literally is not telling you which class it is based on the features that you have extracted. Right? So entropy is telling you that it's basically your h, which is your entropy function, is p multiplied by log p of your probability function. So our goal is to select those data points which have the highest entropy or which have the highest information content. Right? It's very similar to what we are talking about here. Hopefully this particular data point has the most amount of information for this particular distribution because it's very hard to classify. And that is essentially what we are looking for in these difficulty-based strategies. So we select the most difficult samples, so annotate samples with the highest entropy. Right? So if I were to show you a 3-class classification and create this kind of a toy data set where every single point here exists. This is basically not based on actual data, but it's based on creating just a function of generating these continuous distributions of data. So at this point, let's say this is class 1. This point is basically 1, 0, 0. So for this particular class, it is 100% confident. The network is, let's say, 100% confident that it belongs to class number 1. The bottom left here is 0, 1, 0, and the bottom right is 0, 0, 1. This is what this particular graph represents. If my data point falls on any of these 3 points, then you know with a 100% confidence that it belongs to that particular class. But anything in between is unknown. So at this point here, your result is usually 0.5, 0.5, 0. At this point, your result is usually 0.5, 0, 0.5. Again, the zeros are strategically placed so that the third class, this class, has no bearing on the middle portion here, right? So that's why we have a 0 in the middle of this line at this point. So anything on the lines, segments of the triangle itself is going to exist between 2 classes. But come to the middle here, the center. This essentially is something like 0.33, 0.33, and 0.33. At the center is where you have no clue at all which the data point it may belong to. You can think of this again in multiple ways, but the easiest way is as a set of logits. There's also a way where you can consider each of these line segments as a classifier, which implies that anything at the center here, it doesn't belong to either of the 3 classes. But at least from my perspective, it's much easier to think of it as this kind of a probability density, where every single point, the color represents across the 3 different classes. So your goal is, if a data point lies in the center over here, then it's the prime data point for you to actually do the labeling. So if your budget is, let's say, 3 points, and let me put, you have one image here, another one here, and the last one here, another one here, here, let's say here, and here. If you have these number of data points across this distribution and you're asked to select just 3 of them, then the ones that you should select are this in the middle, these 2 in the middle, as well as one of these. I didn't draw this properly, but maybe this one is closer to the center, right? So these are the 3 data points that you should label, ask the annotator to label, so that you can now put this back in your training set and train your algorithm. So this is how you would do entropy sampling. The next one is least confidence, which is again very similar to, let's say you have a softmax algorithm. Let's say you're considering that to be a confidence, or you have some other confidence metric that you're using. You pass all the unlabeled data through this confidence metric. You'll get a certain amount of, you'll get the confidence for every single data point. You select the ones which have the lowest output probability or the least confidence. So among all data points, you select the ones with the least amount of confidence, and if I were to create a function, generate a distribution out of that, it would look something like this here. See the difference here? This is more of a spread out distribution because of the way entropy is designed. Least confidence, on the other hand, has a more structured, triangular structured distribution in this particular case. Again, the goal or the idea here is to sample data points with the lowest output probabilities. If you're 100% confident about something, then you don't really need to label them. But if you're 5% confident about something, that means that it's good for you to actually go through and do the labeling portion. So that is the kind of intuition behind using something like least confidence in order to select your data. The last one is margin classifier. Similar to what we had discussed before. Margin is this idea that if I have a classifier, something like this, I want to make sure that there is a margin that exists between the closest data point and the classifier. In this case, I can have this as my margin. I haven't put this line properly, but here, there should be some distance here between the margin and the data point itself. In this case, the margin that we'll be looking at is between the predicted class, let's call it CS, and the next highest prediction in terms of class, which is the CH. Right? So when you have a prediction that you can make, let's say it's a 10 class prediction, you'll get a 10 cross 1 output at the very end, and you put a softmax classifier on this, and you'll get a 10 cross 1, right? And once you get the softmax 10 cross 1, you take like an argmax, which is going to be your highest probability, and you're going to use that as the prediction. In margin classification, you choose the highest as your prediction, and you find the next highest and take the difference between them. And that is going to be your margin. You're going to use that as the, let's say, feature within your framework in order to now select the ones which have the lowest margins. So if there is a large margin between your prediction and the next best prediction, that means that it's probably a trustworthy prediction, that it's a good prediction, you really don't need the label for it. But if, let's say, the margin between the predicted class and the next highest prediction is very, very low, then that means that there is some kind of difficulty that the network is facing. Right? So that means that you would need a label for this particular data point, and you would use that within and you would use that for the oracle to label, put it back into your training pool, and retrain your network all over again with this kind of small margin data points. Any question? And this is, on the right-hand side, is the probability density for what your margin is going to look like. If you analyze these the equations, by the way, this is what the probability is going to look like, which implies that in this case at least, if a data point exists at this and at this point, then both of them have the same result. So at this point and this point, you can choose either of them and they'll still work. And give you the exact same information if you were using a margin classifier, right? And that is true, in fact, in this part as well. So if I have something here and here, both of these are exactly the same. This was not true when we talked about entropy, right? So this, if you had a budget of 2, then you would choose this and this, but you would not choose this, because the middle ones are the most informative according to entropy, but that is not the case in margin. All these 3 have the same set of information that you would be looking at while trying to create your acquisition function. Any questions? Yes?
By selecting the images with the most or with the least confidence, or they could be potential outliers, do you run the risk of overfitting model?
You do run the risk of overfitting models to outliers and anomalies. And in that case, it's very bad because your network usually is not able to learn much from anomalies since they're so far off. And that's why next I'll come to diversity-based strategies, where you do the exact opposite, and fusion is actually a combination. The ideal way is that you choose some of them which are very representative and some others which are kind of outliers from least confidence. Yeah. All right. The next set of functions that we'll discuss is something called diversity-based acquisition functions. And for this case, these are called this because we select samples that best represent the data. So in this case, let's look at this image here on the top. You have multiple data points that span the entire representation space in this case. The ones that we were interested in terms of least confidence or entropy, would be something like here. But I think as the question pointed out, which was absolutely correct, which is that if I were using just these points, then maybe this point here as well, right? So if I were just using these points, then I would probably overfit to these anomalies, and my network might not even learn anything from anomalies, since they are very difficult to begin with. It's not able to extract the relevant information and train your network. A better strategy might be using some things that represent your entire data set, which is when we talked about k-means clustering, for instance, we started off by assuming that there is some centroid and then started creating distances, right? So we start by creating these kind of representative data points for this particular class or this data set, and say that I want to train on these the representative samples. In other words, these could be the simplest possible samples from a particular class or from a particular cluster, and we want to use them in order to train algorithms. Now, you could do the exact opposite of what we did, which is you could have taken the least confidence, or you could have taken the most confidence, sorry, the least entropy, or the most amount of margin. That could be done, but generally they have been shown that they're not very good strategies in terms of active learning. So this is where we come to a little bit more deeper analysis. First algorithm we look at is course set. Again, the idea of active learning came from a very theoretical community. So that means that if you start reading papers from back in the 1980s, you'll see that it's a very theoretical set of papers. It's all about equations. It's all about trying to come up with bounds to say, oh, this is the upper bound in terms of what is the maximum performance that I can get out of this, let's say 40% of the samples and so on. So most of these theories come from there, and many of them have nothing to do with deep learning, even though we are doing this at the tail end of deep learning, literally the last class. A lot of these algorithms don't have much to do with deep learning themselves. So course set is one such example, where the idea in course set is, given this kind of data points, you can simply do a k-means clustering on the data to select the best centroids or the best, most representative samples in order to construct your data set. So you start off by making this kind of centroid. I'll use the same terminologies I'd used before in k-means, but those are not the same terminologies we use now. But these are the kind of centroids that you choose. Then you create this kind of a distance function. In this case, in course set, we call that a loss function, and this loss gets accumulated. So this loss here, for the leftmost cluster, you have about 6 of these losses, all of which get accumulated, which is exactly the same as the update step that we were using within k-means clustering. All we are doing is just constructing a bunch of distances and adding them together and saying that this is the accumulated loss that can exist. And we loop the same thing until convergence. We add the sample with the highest utility to the subset. So basically that means that if a particular data point, we see that it's adding too much loss or distance, it needs to go to a different kind of a centroid, we do that. This now moves to a different centroid, and we now construct the same thing over and over again, and we loop until a particular convergence in order to find the middle point. Right? Now, generally, when the papers were constructed, it was for something like the data points themselves. But these days, when you use it for deep learning algorithms, you take the final fully connected layer, or just the features before the final fully connected layer, and you can construct these kind of course set, or more simply put, something like a k-means clustering or algorithm on top of it, and then you'll be using those clusters, the cluster centroids, as the representative data points. Right? So all you're doing is taking the outputs from the previous last fully connected layer or the one layer before it, and constructing a k-means and saying that these are the representative data points. Please label them for me, is what you'll ask the annotator or the oracle. And once you have that, you'll put it back into the training set, and you'll go through and construct your algorithm as before. The last strategy in terms of the diversity-based acquisition function is something called discriminative active learning. In discriminative active learning, the way we do stuff is we construct a binary classifier to say if something is labeled or unlabeled. So think of this as a pretext task. So in self-supervised learning, we constructed these pretext tasks that have nothing to do with the labels themselves, right? This is something that we do here as well, which is we'll construct some kind of a very simple one-layer classifier on top of either our data points or our outputs from the final and fully connected layer with the label that it's either labeled or it's unlabeled. So in the beginning, I have about 1 million images, all of which are unlabeled data. I have about 128 images that are labeled, right? This is what I start off with. Or maybe this should have been 999 something. I'm just going to train a very simple classifier on top of the labeled and unlabeled. And I'm going to use the probability from this classifier in order to say whether I need it for my next selection of subset or not, with highest probability of being unlabeled. So essentially, I'm just creating like a very simple pretext task and seeing that if there are samples within my unlabeled pool that are very similar to the labeled ones, then it'll give a very high probability in terms of, okay, this image is labeled, but you don't want that. You want to select those labels which have the highest probability of not being labeled, in which case you're saying that, okay, this is something that I do need to label. It's very far from the label distribution. This is something that I need to label, and you'll go through and do the labeling on top of it. Again, usually this is diversity based because we are not looking at the ones which are closer to the labeled outputs. We are looking towards the one which are closer to the unlabeled, which are the most unlabeled, let's say, across your training pool. Any questions in these two, the discriminative active learning and core set sampling? All right. Hopefully it's clear by now that neither of these strategies are the best, or neither of these set of strategies are the best. If you come from a more theoretical framework, the difficulty-based sampling makes a lot of sense because you want your network or you want your machine learning model to be able to classify the most difficult ones. And the hope is that once you have classified the difficult ones, it's very easy to do the easy ones. But in practice, it has not proven that way, especially when you start talking about like very large data sets. This has not been the case at all. It's very hard to say what is difficult just based on a labeled set of 128 samples or 1,000 samples. You need a much larger set of labeled pool to actually even start saying if something is going to be difficult or not difficult for a particular network, which has millions and billions of parameters. The ideal way is a fusion of these strategies. We won't discuss about the strategies themselves. There are a number of these strategies that have newer works, I think since 2020, have concentrated more on these kind of fusion-based strategies, where the goal is you label these 4, where half of them are, let's say, from a difficulty-based perspective, and the other half are from a diversity-based perspective. Again, we won't discuss the strategies themselves, but at the end of the presentation, I have a bunch of references. 2 of those references relate to what these fusion-based strategies are. So if you're interested, you're more than welcome to go through them. But fusion-based themselves will not be part of your final exam. All right. Finally, for the last topic, we'll discuss something about deployment. So in a lot of cases, it's very straightforward to think about what deployment means. In supervised learning algorithms, you just learn something, you put it out into the real world. Unsupervised learning algorithm, your goal is never to create decisions, but rather to help interpreters in making certain decisions. Self-supervised learning algorithm can be thought of as like a precursor to supervised learning algorithm, where you learn representations and then use them within meta-tasks, within all possible tasks that can exist, because ideally you've learned a good latent representation space using the self-supervised learning algorithm. Deployment in active learning is a little bit different. And in general, this is usually how deployment works. If it's not a reinforcement learning setting, if it's more of a traditional settings, active learning is the way that deployment works. You have a bunch of data, you train your algorithm on that data. Next, you add a little bit more amount of data. Let's say you're an autonomous vehicle company. You have had about 50,000 hours of testing on the roads. You have all that data, you've labeled it, you've trained your algorithm, now you deploy it. If you keep deployment schedule on track, which means that by another 10 days, you might have another 50,000 hours of data available to you, because at every single instance, you're still recording from your autonomous cars, right? So now you cannot take that 50,000 hours and put it back into your training algorithm and say that I'm now going to train on 100,000 hours of data. You cannot ask some labelers to now go through and label those 50,000 hours, because the next week you can have another 50,000 hours and so on. So you need to start picking and choosing essentially the data points that you need to label, and this is where the active learning part comes in. From a deployment perspective, usually when we started off by saying 128 images I'm randomly choosing, that is incorrect. I choose the highest amount of data, let's say 1 million images to start with, but then I keep getting more and more data. At this point, I cannot choose all possible data points for labeling. I need to start picking and choosing a smaller amount of data. Now, the goal in deployment is to make sure that your performance keeps on increasing. If there was no accident in week 1, you shouldn't have an accident in, let's say, week 5, if you were presented with the same driving conditions as you were presented before, right? And this is essentially where this idea of performance regression comes in. So if you have this particular scene, the first few slides are again more of an example or motivation and not real data. But from this perspective, let's say I have an accuracy of 87% in this particular scene. There is one, maybe I'll show the next one. So you see this particular car here, this has not been labeled. You see this particular car here, it has not been labeled. But if I go to the next one, let's say I now have access to another 10,000 more hours and have trained everything again. And if I've retrained it, you see that this car has been correctly classified. This car at the background has also been correctly classified. But you have missed one thing. This pedestrian who was here was classified correctly in round, let's say, n-1 to get a lower accuracy of 87%. If you, at round n, with more training, if you have gotten a better accuracy, which is 89%, but you have now missed the pedestrian. So this is what we call performance regression. Based on what the performance was in round n-1 or the previous deployment, your current deployment is worse than what it was before. So this is called either performance regression, or in other cases it's also called software regression, where any kind of update that you're making is now going to be problematic. And it doesn't always have to do with accuracy. I read a recent paper from Amazon where the way they talked about it is that from a search functionality, in your photos, if you want to search something and bring someone up, let's say till now you have been using a certain terminology to bring up a particular photo. Let's say it was incorrect from the perspective of a network, and it has now corrected it. So when you create that search term in your Photos app, it won't be able to bring back that image again. And in your mind, it's now acting weirdly. It's not acting how it was supposed to, even though from a performance perspective, from the network perspective, its accuracy has increased. So that is where the software regression has happened. And in most deployment cases, this is a very problematic case. And especially if you're doing active learning setting, where you're only selectively taking out certain data points from the later stages of your training. Right, so regression refers to the deterioration of performance after updates and puts model predictability at risk. So every single update that that Apple sends to your phone, for instance, there is certain amount of risk that is involved with it because it might be changing something within the software itself. And if it was a learning algorithm, then maybe something is getting worse than it was previously. That is what we usually call as performance regression or software regression. So in active learning, it's important, the stopping criteria, the deployment decisions for online learning and active learning, and the protocol quality are very, very important when we discuss these kind of performance regression strategies, or when we discuss this idea of updates and deployment itself. And one way to try to measure this in terms of learning is by the idea of negative flips. So let me try to explain what this graph means. So at round n-1 and round n. So think of this as when we looked at the performance metric graphs, round 3 and round 4, right? This is essentially round n-1, round n. So at round n-1, you had this kind of a classifier. If you look at the number of images that were incorrectly labeled, this was incorrectly labeled, this was incorrectly labeled, this was incorrectly labeled. So 3 of them were incorrectly labeled. Now you move on to round n, where you have a new classifier. And at this point, all these 3 things are now classified correctly, but these 2 have regressed. In other words, they were classified correctly before in round n-1, but they have now been classified incorrectly in round n. Now, the overall accuracy has increased between round n and round n-1 because these 3 images have been classified correctly. The overall accuracy has increased, but these 2 data points are problematic in that they have regressed. So this is what we call negative flips, and these negative flips are a very, very, very important criteria when we discuss about deployment strategies, where if we want to measure regression, then negative flips is a good way to measure it. So in terms of active learning, this comes down to the idea of negative flip rate. So it captures this kind of performance deterioration after updating the model. In other words, when we talked about the performance metrics, we talked about accuracy, false positive rate, true positive rate, but we never discussed about this idea of NFR, which is the negative flip rate. So you can go back and put NFR as the y-axis within your performance metric as well. Essentially, it's the number of flips that have happened. So y old equals yi. So in my update n-1, what exactly was the number of true positives, let's say, that has now been shifted into the false positives in round n. The difference between the 2 is going to be the negative flips. So in this simple case, it was 2, and this exists, in fact, in all algorithms. So if I were to show you an example, so generally accuracy, this is what we saw in performance metrics. This is how the accuracy keeps on increasing with more rounds. We expect that the NFR is going to decrease like this. And in some datasets, that is true. This is in CIFAR dataset, forget at 0. At 0, basically, there is nothing, no decisions. So what you see is that you have this kind of a decreasing trend in CIFAR 10 in terms of NFR. But on CIFAR 100, this keeps on increasing. In other words, more and more rounds that you go through, your results when your acquisition strategy is entropy, least confidence margin, your performance, even though your accuracy is also going to increase, it far outpaces the amount of negative flips. There are negative flips that exist within this framework. So it's very important when we discuss about deployment that we are very sure what we are looking for. Just a very simple accuracy is, and even something like F1 score is not going to be sufficient. When it comes to deployment, there are its own challenges. And within active learning especially as well, because generally this is a favored approach in terms of how we can do deployment. Our goal is to do some kind of selection within new data that keeps coming in. All right, so again, the last part is the appendix. So that is the end of lecture number 26, and that is the end of all lectures as well. And as I mentioned at the start, it is probably going to be the end for about half the course, about all grad students, because you'll be submitting your project report today, and that is it. If you're not taking the exams, that is it. By the end of this week, we will release the grades for everyone who is not taking the exam. So you'll be able to see, and if you have any questions, you can email me essentially about that. Best of luck for your exams if you're taking it. Otherwise, have a good summer. Thank you.